Good morning and welcome to another Physics with Keith on a Sunday morning, somewhere in Essex under the stairs. This week we're going to be looking at forces and acceleration. I'm trying out some new software as I often do, so that's why the background of the chat is a different colour this week. But that's the only main difference. I can see we've already got a few regulars tuning in. Good morning, Freya and Wombat. Ted has tuned in as well. Annabelle's come along. She said she loved last week, but I don't remember seeing you. Lex is in. Hello, Lex. I missed you last week. It's good to see you again. So let's get cracking with this then. Just like last week, I've prepared some things in advance and I'm going to be displaying them as I go through. But as with any session, if there are things you want to go through or if there's anything where you're not quite sure and you want a bit more guidance, then just let me know. Thanks, Wombat. Yes, it is, Ted. There's a link somewhere on my YouTube or on my website. Anything that you want me to go into a bit more detail, I'm doing this session for you. So just let me know and I can always sidetrack. So this is the session this week that I've planned out, which is forces and acceleration. And Ted already said that he had a bit of a look over this topic already. It's such a fundamental topic for everything we do in physics. So I imagine that this is going to be something that is going to crop up again and again and again. And it's all based around one equation, this session. And the equation was introduced last week. We basically derived the equation from Newton's second law last week. The equation is this one here. So before I do anything else, I'm going to give you just a moment to jot the equation down in case you need to. Although on all the important slides, I popped the equation just, I think it's about there on the slide, just to help you out. Now, some things to note about this about this equation. It comes from Newton's second law, where we had that the rate of change of momentum is proportional to the resultant force. All the way through this, I'm going to try to make sure I call it resultant force, not just force, and that's quite important. And the session next week, we're going to be looking at vectors and getting a better understanding of why I'm so fussy about this F being called resultant force. Unit for force is the same as the unit for mass multiplied by the unit for acceleration. So the unit for force is kilograms meters per second squared. So that's equivalent to newtons. So 1 kilogram meter per second squared is 1 newton. So that's all I wanted to show you on this slide. So it's time now for us to move on to a quickfire round. Just before I go into the quickfire round, Ted had a question. SI unit of, what is the SI? So SI means System International, or which is French for international system, I guess. It's the international system of units that we all agree on. So when we say the SI unit, we just mean that is the unit that everyone across the whole world agrees we're going to use. The SI unit for temperature, for example, is either the degrees Celsius or the Kelvin. They're both SI units. There are countries, however, that prefer to use degrees Fahrenheit, but that's not an SI unit. They're going against what every other country in the world has agreed. SI unit for distance is the meter. But there are countries that prefer to use miles and yards and feet and all this sort of nonsense, whatever they are. So that's what SI means, Ted. It's just what we all agree. Okay, let's move on to the quickfire round then. So what I want you to do is to try to answer the question. Feel free to show you're working on a piece of paper if you want to. Otherwise, just answer the question, and as soon as you've got the answer, bang it straight into the chat, and we'll see what you come up with. Oh, there's a few new people. Pooja and Adam, good to see you. Yep, some great answers. Yep, 20 newtons, definitely 20 newtons. Force is mass multiplied by acceleration. Mass is 2.0, acceleration is 10, so 2.0 times 10 is 20. Good. So, Ted, do you see where you made your mistake? Yeah, you divided. Exactly. Yep. And Gavin, well done for popping the unit on there. Definitely need to have the unit. So we're moving on to question 2. It starts easy. It will get more tricky. I'll just show you the working, but there we go. Oh, something with the working. Something I like doing, and if you were here last week, you saw it then. I like writing the numbers with the units and then separating out the units. And I do think that's important to do. With more complicated questions, having all those units bunched together really does help you keep track of what the unit should be for the final answer. So in this case, kilogram meters per second squared is newtons, but I've left it as kilogram meters per second squared for as long as I could. Okay, let's have a look at question 2. As soon as you've got the answer, pop it into the chat. Okay. Oh, Jack's turned up. Hello, Jack. So you can see some of you are getting a buzz to mean you're wrong. Some of you are getting a ting to mean you're right. And yet, some people might think you're all giving the same answer. Exactly right, Pooja. Yep. So why am I giving my answer to 2 significant figures? So you all remembered the kilograms, which is wonderful, but why am I giving my answer to 2 significant figures? Good morning, Lucas. Why am I giving my answer to 2 significant figures? Yeah, perfect. It's not just that it's the lowest number of significant figures in the question, Jack. It's the lowest number of significant figures of the data that we're using in the calculation. Yeah, exactly, Frey. You've basically got it there. But if I've got a question with lots and lots of different numbers on it, but I'm only picking 2 numbers out for the calculation, then it's the lowest number of significant figures of those 2 numbers. That's what matters. So yeah, 2.5 is 2 significant figures, 2.5 meters per square second. Okay, let's move on to, I'll show you the working in case you want to have a look through it. And you'll notice that I've done something here. I gave this part to 3 significant figures. I kept an extra significant figure, which is called a guard digit. And I kept that guard digit in case there was anything, in this case it was quite a simple calculation, but in case there was anything funny going on with the rounding, then I would use the unrounded number in a subsequent calculation. If I needed to use this 5.0 kilograms in a second part of a question, then I would use the extra significant figure, so that if there is a rounding error that would accumulate, it will accumulate on the missing significant figure, the one I'm rounding off again anyway. So how do you get to m equals f over a? Okay, let me just grab my little whiteboard out. And my special whiteboard pen. Switch across just for a second. So our equation was f equals ma. Hopefully that's just about on the screen. Yeah, that's just about on the screen. We wanted to make mass the subject, this thing here. So we have a look what's happening to the mass. The mass is being multiplied by the acceleration. So I do the opposite of multiply by acceleration, which is divide by acceleration to both sides. And if I divide this side by acceleration and that side by acceleration, I can see that the accelerations cancel. So what I'm left with is just my mass, which is equal to force divided by acceleration. Yeah, exactly, Ted. So you just have to be a little bit careful about what the subject is that we're after. The subject of this equation was the mass, so we want to get the mass all by itself, so we do the opposite of what's happening to the mass. And what's happening to the mass in this case is it's being multiplied by acceleration. Okay, let's move on to question 3. Quick fire round still. Some great interactivity today. I'm really buzzing on this. This is brilliant. Ah, I put a ding then when I meant to do a buzz for Lex. Sorry, Lex, it's not meters seconds squared, it's meters per second squared. So you did a little minus in there. That's possibly just a slip of the key. Annabelle, unit for acceleration is meters per second squared. Again, I imagine that's just a little slip of the finger there. Freya, great. Gavin, yep, okay, we're all good. We're all good. We're all giving the same answer. So here's the working in case you want to go back and look through it at some point later. Remember, all these sessions are recorded. Well done, Ted. We wanted acceleration. Acceleration is being multiplied by mass, so I divide through by mass. That's where my force divided by mass comes from. Plug my numbers in. I turned the newtons into kilogram meters per second squared there. And I did that for a reason. I did that because I can see what happens to the units. That's a nuisance. I'll just put the 2 then. You can just type the 2. I know what it means, Annabelle. That's fine. So you can see here, I've turned the newtons into kilogram meters per second squared, because that way I can see the kilograms on the top of the fraction and the kilograms on the bottom of the fraction cancels out. It might be better if I show you what I mean. Where the fractions stacked up properly. So on that line we had 68.6 kilogram meters per second squared, and I divided that by 7.0 kilograms. And now you can see very clearly the kilograms cancels, leaving me the unit meters per second squared. So including those units helps you navigate your way through the question a little bit, I think. Okay, so question 4, quick fire round still. Adam corrected himself. Wombat's corrected himself as well. Ted, your unit's incorrect there. Yep, okay, so we're basically there. So the reason why Ted's unit's incorrect, remember that a ton is 1,000 kilograms. So this mass here, the first thing we're going to do is to convert units. We're going to do that before we do anything else. Half a ton is, I'll do the finish off the conversion. Half a ton is 500 kilograms. And the way I've done the conversion here might look a little bit grungy. I've done my mass multiplied by this thing in the square brackets. Yeah, Ted, that's much better. That's much better. Well done. So this thing in the square brackets is the number 1. If 1,000 kilograms is equal to 1 ton, then 1,000 kilograms divided by 1 ton is just 1. And 1,000 kilograms is a mass, 1 ton is a mass, so the massness cancels out as well. So we're not actually changing our mass at all by multiplying by the number 1 that has no dimensionality of its own. But it means I can cancel the tons, because I've got a ton on the top of the fraction and a ton on the bottom. And if you want me to write that out in a longer way, I'm happy to do so, but you might get it. And if you get it, I won't bother. Just let me know. So now I've done my conversion, F equals MA, plug the numbers in, and carry on with my calculation. Now, the thing to be careful of here is you've converted your unit for tons into kilograms, and you've probably written it as 500. If you forget, that's still only a two significant figure number. So sometimes it's more sensible to write this in standard form, 5.0 times 10 to the 2, so you don't forget the number of significant figures. The mass was only two significant figures, even though we've written it as 500. So when you get your final answer, that's not correct. We would use that answer in any subsequent calculations, but if this is the final answer, we have to round it to the right number of significant figures. It just fits on the bottom of the screen there, which is 840 newtons, two significant figures. Okay, the penultimate quick-fire round question. Let's go. This is a sort of question that does start to stretch Year 12 physicists as well. On the face of it, it's no more difficult than the other questions we had before. It is a GCSE level question, but there are some extra complications in it, aren't there? Antonio. Jack. Freya. Adam. So you're starting to see where your mistakes are, I hope. Some of you, so Wombat, Antonio, Freya, you've rounded your answer to two significant figures, but the data I'm using in the calculation is three significant figures. I've got to work out whether Ted's correct now. I think Ted's is correct, although he hasn't included a unit. Gavin's fine. Lex is fine. Yeah, the other thing is, Freya, it's you've got these complicated unit conversions to do as well. So let's do these unit conversions to start with. We're going to start with the acceleration. Well done, Ted. So if we start with the acceleration, 65.0 centimeters per square second. The centi part is the same thing. Yeah, Freya, and do you know what? That's really common for people to find it difficult. That's why I'm trying to include every week some questions where there are these unit conversions. And I've in fact made a unit conversion drill that that you can use to get better and better and better at it. If you are on the regular participants Facebook group, and I'm not sure if you are or not, but if you are, then you get free access to those question generators. And you know, this is your area of weakness. Brilliant, you found it. Now we can get some practice up. Although I know you've got a few years until your exam. Oh, promised I wouldn't say that word. So you don't have to worry about it if it's not urgent. But you know what? It's good fun as well. Anyway, so 65.0 centimeters per square second. Centi means 10 to the minus 2. So you just plug that in and you end up with this acceleration in meters per square second. But I also have to convert my force, 48.8 kilonewtons. Kilo means 1,000, so that's 48.8 thousand newtons, 48,800 newtons. Now I can do the rest of my calculation, and I write notice every time I'm writing the equation, then I'm rearranging the equation, then I'm substituting the numbers after they've been converted. Then I'm going to, newtons I don't like, so I'm going to turn that into kilogram meters per second squared. Then I'm going to do the calculation. I cancel the meters per second squared. But then that answer is not the appropriate number of significant figures. So I round it to, in this case, 3 significant figures. And again, it just fits on the bottom there. About 75.1 tons or 77 75,100 kilograms. Both answers are fine. Last question from the quickfire round. Of course it is, Jack. Brilliant. Yep. Well done, Adam. Brilliant. Well done, Lex. Well done, Wombat. Great. So, well done, Antonio and Ted. This is good. This is going well. So, just working through the working. Mass, I need to convert it into kilograms. Force, I need to convert into newtons. Well done, Freya. Then use this equation. I'm after the acceleration, so rearrange it. Substitute my numbers. We know that I don't like using newtons. I like calling it kilogram meters per second squared, because that way I can see clearly I'm cancelling the kilograms, and then I get my answer, and it's already to two significant figures. So, yeah, brilliant, Pooja. Good stuff, Gavin. Well done. So what we're going to do now... Oh, I suppose I should probably say that's the end of the quickfire round. That is indeed, Ted. That is one gravitational field strength unit. It is. That's just the acceleration due to gravity. Oh, Angel, hello. I didn't see you here before. Congratulations. Well done and welcome. Good morning. So we're going to move on now to a little bit of a section about practicals, where we're going to have a look at some standard sort of practicals you might do to investigate this equation and to convince yourself that this equation is correct. There's not a lot of interaction in this little bit here. I'm going to ask questions, but there's not any formal questioning yet. And then at the end of this session, I've got a few good questions that I've managed to get from OCR. They've given me permission to share some questions, which is lovely. So let's start with the basics. A graph like this, resultant force on the y-axis and acceleration on the x-axis. What do you think the gradient of this graph would be? Of course it's the mass. Well done, Jack. Yeah, of course it's the mass. And it's the mass, yeah, thank you, Adam, the mass of the object, the mass of the body that is being accelerated by that resultant force. Well done, Pooja. It's not necessary. Oh, it is in kilograms. You're absolutely right, Antonio. It is in kilograms because the y-axis is in newtons and the x-axis is in meters per square second. Well done. Good stuff. So if we have a look at this equation, it's already in the form y equals mx plus c. Now, if you're watching in a different country, then you're not going to really understand what I'm going on with, what I'm talking about with y equals mx plus c, because in some countries they use y equals ax plus b, where a is the gradient and b is the intercept, and some countries use y equals a plus bx, where b is the gradient and a is the y-intercept. But it doesn't matter which of these equations you use. It's the same idea. I'm going to stick with this one because that's what I'm more familiar with. C is 0 in this case, because in the equation F equals ma, there is no term added on. Now, this is telling us that when the mass is constant, we expect direct proportionality between the force and the acceleration. That's why we get that straight line. So in any sort of experiment, if we have mass as a constant, then we'd expect a straight line on a resultant force versus acceleration graph, if mass is a constant. So let's have a little look at an experiment. Experiment 1. In experiment 1, we have we start with this equation, and we are going to assume mass is constant. So in the equation, m equals mass in kilograms, Gavin, absolutely correct. That's the SI unit. But listen, you could have mass in grams. You're just going to have a conversion in there as well. No worries, no worries. So if we are investigating F equals ma, where mass is constant, we can just take this equation as it is and plot F on the y-axis, the resultant force on the y-axis, and the acceleration on the x-axis. And so the experiment might look something like this. You draw up your table with resultant force and acceleration. You plot your graph underneath it and expect a straight line. Gradient is mass. And a pretty typical way of having a situation where you can change the force, the resultant force, that's the independent variable here, is to have a mass suspended over the edge of the bench from some sort of jockey wheel here. And when you let go of that trolley, it's going to accelerate to the right. But remember, we want mass to be constant. So I can change... Exactly right, Pooja. The resultant force is directly proportional to the acceleration if mass is constant. Now, I've seen this practical delivered by very, very good GCSE physics teachers. Incidentally, not at the school where I work, but in other schools where I have done observations and worked in the past, and they've got this bit wrong. So that's why I think this is quite important to pick up on. If mass is constant, you cannot change the resultant force by... Well, you can change the resultant force by just changing the mass you suspend over the edge of the bench, but that's also going to change the mass that's being accelerated. When I let go of this car, the trolley is going to accelerate to the right because of that resultant force, and this mass that's suspended over the edge of the bench is going to accelerate downwards because of that resultant force, which means all of this is accelerating. I'll show that in animation again because I spent a long time on it. Smooth. So if I want to change the resultant force, yes, I change this mass that I got suspended over the edge, but I don't want to change the mass of everything in this picture. So what I do is I put that mass I've taken off the end here onto the car and strap it down so it doesn't move. And now I accelerate, and then I take some more mass off the end, put it on the top of the car and accelerate. I take some more mass, accelerate, take some more mass and accelerate. And each time I do this, I'm going to take the resultant force and I'm going to determine the resultant force by knowing that acceleration due to gravity acting on this mass that's suspended over the edge is about 9.8 newtons per kilogram. So if I've got 1 kilogram here, I'm producing a resultant force on this car of 9.8 newtons. Or am I? We'll come to that in a second. So, yeah, we stack up the mass on the top of the car so it's not missing. We don't just take it away because then we wouldn't have a constant mass. Such an important step that loads of people miss out. But I haven't missed it out. So you've had that step. So you've done that practical, and I've just hinted at the fact that the resultant force may not actually be the force, the weight of the mass that's suspended over the edge. Ted, you're correct, although I wouldn't use the word slower the acceleration. I would say the lower the acceleration. The word slow, to me, refers to a speed, and a speed of an acceleration doesn't make any sense. So I would say a lower acceleration. Yeah. So I suggested that perhaps this isn't the resultant force, didn't I? And you can calculate the force, the weight, as we've just said, by having this additional mass that's supplied. I'm going to use a capital M for that, multiplied by G, and we're going to say that's F. But is that the resultant force? So we've got applied mass, M. Calculate that. Is that the resultant force? What do you reckon? No. Obviously not, because if it was, I wouldn't be making a big deal out of it. Why not? Type your answer. Why do you think... And if you don't know, just say, I haven't got a clue. Why is the force, this F, produced by this applied mass M, not the resultant force on that trolley? Not quite, Wombat. No, we can make the picture easier by just imagining everything's in a straight line. So, as a nice guess, but not quite. We could talk about magnitude of resultant force, magnitude of acceleration, if we want to clear up the issue with vectors. No, Lucas has got it. Adam, no, that's already taken into account. Pooja, no. Freya's not sure. Jack's got it as well. So Lucas and Jack have got it. Well done to you two. I've got a little sound effect that's appropriate for you two. I hope that sound played. Yeah, friction, Jack. Exactly right. Yeah, friction. Okay, so how can we compensate for that? What we do is we elevate the ramp. Yeah, exactly. Friction. Well, I can't do much about the friction of the pulley wheel, Gavin. Not a lot I can do about that, but you're absolutely right. I can have a well-lubricated pulley wheel. That's about the best I can do. Moving along a surface which gives external force of friction. Exactly right, Teddy. So what I can do is I can lift up the ramp on one end. I don't want to lift it up too much. If I lift it up too much, there's going to be too large a component of gravity acting along the ramp downwards, accelerating the car as well. But when I apply this force, there's a force of static friction in the opposite direction. And as long as I've got a component of gravitational force acting down the ramp, which is equal in magnitude to the static friction acting up the ramp when I'm pulling it, then the force here is as close to my resultant force as I can get. And how do I find the perfect angle of the ramp? Sorry, there's a question here. How could you work out how much friction there is on a pulley and lift up the ramp a bit more? You could do, Gavin. Yeah, you could. I'm not sure I'd want to do that, but I suppose you could do. It's such a minor amount, I don't think I would bother. It's going to be a systematic error on my results. A systematic error on my resultant force is going to shift this graph, so I probably wouldn't bother. But the friction from pulling the car along, that's a bit more significant than the friction of the pulley, I would say. So what you would do is you'd lift up the ramp to just the moment before the car starts rolling. And then you would drop it back down just a teeniest bit. So the car is about to roll due to gravity. At that point, the gravitational force acting down the ramp is equal in magnitude to the static friction acting up the ramp, because any more gravitational force down the ramp causes acceleration down the ramp. And so that we've compensated for friction on the ramp. We have not, as Gavin said, compensated for friction in the pulley, and that's going to be much, much, much more difficult to do. We're not going to do it. Yeah, exactly. So the last piece of the puzzle in this practical is how do you measure the acceleration? This equation is going to come up, and I'm going to teach you, and we're going to derive that equation in episode 5 on the 31st of January. It's not next session, it's the session, it's not the session after that, it's the session after that as well. Pooja, we could say that's the equilibrium point between gravitational force and static friction. We could say that, or maximum static friction, let's be careful. The equilibrium, yeah. So we're going to use this equation. We're going to derive this equation in a later episode. What about the friction on the wheel bearings and the tyre toughness? That's all covered in this, Edward. That's all part of this. The only thing this doesn't cover is the pulley. So here's a ruler. We can measure the distance the car moves, and we can use a stopwatch to measure how long it takes the car to move. This equation is going to appear. I'm going to give you the derivation of this equation later on. For now, just take it as read. We can now determine the acceleration, plug it into my table, sketch the graph, take the gradient. Huzzah, I've got my mass. Okay. Just be a little bit careful, though, because the mass I've got is not the mass of the trolley, it's the mass of the whole system that's accelerating. So if I wanted the mass of the trolley, then I would subtract from this m, the gradient of this line, whatever mass I was adding. I'll put a sigma here to indicate it's the total mass, whatever mass I was adding in total to accelerate the car. So that's experiment 1. Are there any questions about experiment 1? Ask now, because I want to move on to experiment 2 quite quickly so that we can then move on to some more difficult questions. No? Okay. So, experiment 2 is the same equation, but this time, rather than having a constant mass, we're investigating that equation for constant force. So, what we're going to do is we're going to... Oh, as you add m to the trolley, the friction would be greater. Ted, you are not wrong. You are absolutely correct. I'm not sure what we can do about that other than for every single time we do it, we change the angle of the ramp to compensate for friction every single time. Now, Gavin, you can always ask. You can always ask, Gavin. Yeah, let's go back to experiment 1. As you put the mass on the trolley, friction would be greater, but then we just compensate for friction again. Nothing wrong with doing that. It would, Gavin, but if you want to do it properly and you want to get decent results, you know, that's what you do. This is why you can do the same experiment in Key Stage 3, and then you can do it better in GCSE level, and then you can do it even better at A level. And then you can go on to first year of your degree and you do experiments that you did in your A level, but you're just doing them even better again. The first experiment I did on my physics degree back in 2002, I think it was the simple harmonic motion of a pendulum, which is a standard A-level experiment. But it was the first practical I did for my degree, because we just did it better. Okay, so we'll move on to experiment 2 then. Experiment 2, we've got constant force. This equation here is the same equation. It's F equals ma. And we've put it in the same form, y equals mx plus c. And you can see that if I rearrange this equation by multiplying through by F and multiplying through by A, I get back to my Newton's second law for constant mass equation. But we're not going to have a constant mass. We're changing the mass. So I need the mass as a variable, and that's going to be my independent variable in this case. I'm going to change the mass of the trolley, measure the effect that has on the acceleration, have a constant force applied, and I can check this equation works by determining what that constant force is. The issue is that this is not the only way of rearranging this equation for constant force to get it in the form variable equals constant times variable. Because we could also rearrange it like that. And you can convince yourself that's true as well. Multiply through by force, multiply through by mass, you get back to this equation. And this is F equals ma. But now this is a variable, this is a constant, this is a variable. I'm changing the mass, therefore the acceleration is changing, but the force is constant. So if force is a constant, 1 over force is constant. Or I could rearrange it like this. Again, we've got constant force. So here, the force is under 1. I've written it this way. It's an odd way to write it, Ted. This is exactly the same as acceleration divided by force. But instead, I've written 1 over force multiplied by acceleration. It's the same thing as acceleration divided by force. I've written it like this, and I've used the colours to try to help a little bit so that you can clearly see those 3 parts. This is a variable, it's all in blue. This is a constant, it's all in green. This is a variable, it's all in pink, or magenta. And it's in the form y, in blue, equals m, the gradient, which is in green. That's one of the reasons I did this, because I've got m in my equation and m in the form y equals mx plus c. They're different m's. And x is the a. So this is the equation of a straight line. And I tried to space it out a bit. But there is actually another way. Of course there's another way. Well, we just had a look at this one. Yeah, it's the reciprocal of the force, Gavin. Absolutely right. 1 divided by f is the same as f to the power of minus 1. It's the reciprocal of the force. Well, now the mass, because I just switched to another equation. And it's still in the form y equals mx plus c. This is still a constant, still variable equals constant times variable. And that's not the only way, because I can do it this way as well. And it's, you can convince yourself. In fact, I'll put all 4 of those in a row so you can see them all. They are all in the form variable equals constant times variable. They all rearrange to get back to f equals ma. So they are all perfectly good equations to use for this experiment, where I vary the mass and measure the acceleration. So a reasonable question to ask, which one's the best to use? Type which one you think, and you can just type 1, 2, 3, 4 for the first, second, third, or fourth equation. Which one do you think would be the best one to use? And then I'll let you know which one I think. And there's no wrong answers here, because they all work. It's just I've got a personal preference. So there's a lot of variation here, isn't it? A few of you have gone for the last one. A few of you have gone for the first one. One of you's gone for the third one, which is interesting. Third or fourth because it would be quicker, says Gavin. Yeah, no, I can see that. There's less to do, isn't there? There's only one reciprocal. Okay, well, the first thing I'm going to do is, wouldn't it be reciprocal of mass and acceleration be better? Well, that's what we're now going to have a look at. Reciprocal of mass and acceleration is your one. So you're going for number 3, Wombat. Yeah, well, exactly. They all result in the same answer. So first of all, I'm going to eliminate these 2. And the reason why I'm going to eliminate these 2 is because I'm going to try and keep the independent variable on the x-axis as much as I can. That's not a rule, it's just a general guideline, and there's plenty of times in physics where we'll do it the other way around. But it makes the biologists happy, so we'll go with the independent variable on the x-axis wherever we can. It doesn't matter, so we might as well. And so by doing that, I'm now looking at this and thinking, well, this has got less work, as I think Gavin was saying. This has got less work to do. There's fewer calculations. But it's not just that. If I do it this way and choose this one, the gradient is the control variable. And if my control variable changes, somehow when I'm doing this experiment, the mass starts increasing, and I haven't noticed, I don't know how that would happen, but let's imagine that happens, then I would see the gradient increase. Or if the mass started decreasing, if the force, I don't know why I said mass, still in the previous experiment, my apologies, that's a mistake. If my force started increasing, or if my force started decreasing, and actually it could do, couldn't it? As I increase my mass, my resultant force could decrease due to friction if I haven't properly compensated for friction. And I'd be able to see that quite easily. If my resultant force started decreasing, I'd see the gradient of my line decreasing. And so I'd have that direct information from the graph. Ah, yes, the gradient's decreasing, resultant force is decreasing. I wanted my resultant force to be constant. I need to have a look at my experiment again. So I would go for the third option as my preferred option. But as I say, they all work, so you can use any of them. So same thing as last time. This is the general layout of your experiment. You've got your table, total mass m, and it's the total mass here, or is it the total mass here plus here? Well, yeah, we'll come to that later. Total mass here plus there, but I'm going to add mass on. Then we've got 1 over mass, because that's what I'm going to be plotting on the x-axis. Then we've got acceleration on the y-axis. And you'll notice I have not extrapolated this line all the way back. And that's because I can't practically do that anyway. If I were to extrapolate this line all the way back, I would be saying that I get 0 acceleration with infinite mass for a constant force. Which I suppose kind of makes sense, sort of. And a mathematician would now be screaming at me saying, no, 1 divided by infinity is not 0, and things like this. Well, yeah, you have your undefines if you want. It converges towards 0. So I'm not going to extrapolate this line back. And just as before, we're going to do some friction compensation. Just as before, we're going to use this equation to determine the acceleration. And just as before, we're going to use this. I don't want to dwell on it anymore. I didn't want to use the majority of this session with me talking. So if there are any questions now, might be the time to ask. Because we've got 15 minutes left, and I really want to dig into some larger questions. And that's about how much time I need. No? Okay, good. So they're the two experiments. You'll probably do them at some point if you're at school. Can we not conduct experiments in a vacuum to avoid friction? Wombat, that would avoid air resistance. It would not avoid friction. Where do you take M from? That's a good question, Ted. So in this equation, the force is accelerating the mass of this plus the mass of this. But we're going to be adding mass on to change the mass of this. So we'd have to calculate the total mass as we go through it. But the mass is the independent variable. So we're expecting that we can measure the total mass being accelerated somehow. So this M is not just the mass of the car here. It's the mass of this thing as well. And as that's the independent variable, as I add to it, I add to it. But I can shove this thing here and this thing here, and any extra masses I add, I can shove that on a balance to measure what that is, because that's a variable that I'm measuring, so I'm not worried about that. Okay, we're going to move on to not a quick fire round at all now. We're now going to move on to some more challenging questions. I promised I wouldn't use the E word, so I'm not going to do that. It starts pretty straightforward, and then gets a little bit more challenging as we go through. Don't type your answer. Please don't type your answer yet. I'm going to use the timer. Let's just switch the timer on, which I'm not allowed to put over that disclaimer at the bottom. I have to put it somewhere else. Where shall I stick it? I'll stick it up there. A little timer there to make sure we stay on the straight and narrow for our timing. So let's start with perhaps not 23 minutes. Let's start with 1 minute. In 1 minute time, when that timer hits 0, press enter. Have your answer loaded up, and as soon as that timer hits 0, press enter. So all the answers should appear at the same time. About 10 seconds to go, so stand by to press enter. Okay, let's see your answers. Okay. Well, this is going to make you all very, very sad. Very, very sad, but according to the rules, the guidelines, whatever you want to call them, every one of your answers is wrong. You're going to get very, very grumpy at this. No, you're going to get very, very grumpy with this. F equals ma, fine. We noticed that this number isn't used in this part of the question. You all did that part correct. You knew, so force divided by mass, and you got 3. And you could just use a calculator, or you could do it in your head, because you know you 3 times 10. Yes, Ted, yes. Units are given. I'm not worried about that. I'm very happy for you to give units twice. You don't lose marks for that. Why on earth have I given my answer to 4 significant figures? Yeah, exactly. So this is a 4 significant figure number. I have to assume it's a 4 significant figure number, and so's that. Now, the mark scheme did not give that answer, but according to their own rules, that should be the right answer. All your answers were fine. None of you got it wrong. And you'd all get marks for it, but I just thought I'd have fun being a pedant. It's good fun being pedantic. Right, I hope you have got some of these numbers down, because the next question is going to use these numbers. I'm going to give you just 20 seconds to copy any numbers down from this question you need before we move on to... Oh, I did it again. Before we move on to the next question. So, click, 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 click. 20 seconds to... Oh, no, I've given myself a background. 20 seconds to the numbers. Just write down the numbers you need for this calculation. You're not given an acceleration in that question. You're given a speed, Ted, and you didn't use that speed in the calculation. So those number of significant figures are irrelevant to your final answer. Okay, so moving on to part B. Good luck. 3 marks. Therefore, I'm going to give you 3 minutes. And I'm going to actually change my... I don't like my background. I know this sounds like I'm fussing, but I like a white background on it, not this silly, colourful background. There we go. 3 minutes. Go. As soon as the timer hits 0, press enter on your answer. But don't press enter too early. About half a minute left. Oh, I wouldn't go that far, Wombat. I think what I'm offering is unique compared to what else is out there on YouTube and all the other support that's out there. I think what I'm offering is a little bit different. Okay, everyone hit enter. Fabulous. Pink Dolphin, hello, good to see you. Oh, Tilly's joined in. Hello, Tilly. Okay, that's wonderful. So, no issues there to pick up on. You all got that correct. Nasty thing here, of course, was that you had a final velocity. You had an initial velocity, but you weren't given a final velocity, except that you were told that you are finishing at rest. Ah, Pooja. Okay, well, have a look at my worked solution there. And look at yours and see where you've gone wrong. So let me talk you through mine. I've got my initial velocity. My final velocity is 0 because we finish at rest. That's what it said in the question. My acceleration is in the opposite direction to my initial velocity. So that's why I've put a minus sign on there. This is the definition of acceleration, and we will do this in a few weeks' time. We're going to derive all these equations from first principles. But we want the time so that we can plug it into the equation that I showed you earlier in this session in order to get your answer. Now, A-level students will have already, possibly at this point, derived S equals ut plus a half at squared and all this sort of thing. Freya, I hadn't thought of that. Yeah. The thing with yours, Freya, I'm not sure why yours actually works, because what you've said there, d equals st, I think you mean s is speed. So that would be d equals vt, or s equals vt, which is correct, but your 3 is the acceleration and u is the speed. So I think it's just pure luck that yours has worked there, Freya, because the equation you've typed doesn't match the numbers you've put. Oh, how do I know u is that? Because it was in the previous part of the question. Yeah, well done, Wombat. So Freya says, yes, I was just guessing, really. I didn't actually think it was lucky. Yeah, you're very lucky. The nice thing is that if you were to do that in a, I'm not going to use the E word, situation, then as long as your answer on the line is correct and there's some working, at GCSE level, you're going to get full marks. But we want to do it formally. We want to make sure we've understood it properly. This is probably a bit of a long-winded way of doing it because I wanted to show how you could get there without having to use the data sheet that you would be given. And there's much quicker ways of doing it by using the data sheet. There's an equation v squared equals u squared plus 2as that you could use instead. But because I haven't done the equations of motion with you yet, I just wanted to use those very basics. This equation I gave to you earlier in the presentation, although I just skipped over it, this is the definition of acceleration, which I've probably done in a previous session. But yeah, it was a tough question. It is a tough question. So this part here for 3 marks. So I'm going to give you, I would usually give you 3 minutes, but I'm pushed for time here. So I'm probably just going to give you 2. Good luck. So you're going to type your answer. Ted, you can't subtract. The 3 is 3 meters per second squared. The 18 is 18 meters per second, and you can't subtract 18 meters per second from 3 meters per second squared. They are dimensionally different quantities. What I would suggest, Ted, because that was, the previous question was quite advanced mathematically, have a look back at the video and pause it at that point and work through the mathematics a bit. I'll try to lay it out with every step. Track where the numbers are going, that sort of thing. So you're all typing your answer, frantically typing your answer to this. About half a minute left. Yeah, it's slowed down 3 meters per second every second. Okay, hit enter, everyone. Just hit enter. Doesn't matter if you're finished. Doesn't matter if you're partway through your answer. Okay, so we've got the idea of less resultant force from Jack. No, it's not a silly answer, Gavin, not at all. And there are other, I've seen questions where that's the sort of thing that's being asked about. Not in this case, but I have seen that. Okay, so you've got some great ideas. Here was my solution. Here's my answer. A little thing about how I've written it. And I know you couldn't really do this in the chat. I'm not sure if you can hold shift and press enter to start a new line on YouTube chat. I'm not sure how that works. But I always start a new line with something that I think might be another mark point. I always do that. And this was a 3-mark question, remember? It said it in the bottom corner here. So my first mark point, I thought, they're using a vague word. No, you can't. No. Okay. So in a written situation, I would start a new line for everything. They're using a vague word here. They say, explain whether the distance traveled with a car stops is greater than, smaller than, or the same as. So they're saying explain why, and they're being vague about whether it's greater than or smaller than or whatever. They could have just said, how does the distance change, being vague. Okay, thanks, Gavin. So what I did, I went straight to writing the answer to start with. Distance is greater. And I think, I haven't checked the mark scheme, but I think that's right, and I think you all agree with me with that. Now, the gravity is acting in the opposite direction to the braking force. The braking force is acting up. The gravity, there's, as I said, a component of gravity acting down the ramp. And that means the resultant force is lower. And from what I saw, you all said that the resultant force is lower, which is brilliant. In the past, I've seen a lot of people saying the opposite. And then the last point here, I thought, let's throw a little bit of maths at it. So I threw the S equals a half AT squared from the previous part. We got that equation just by rearranging the equation I showed you for acceleration last time. Acceleration is 2s over t squared. If the force is less, acceleration is less. Therefore, for the same distance, the time has to be more. Or whatever, I don't know what I wrote there. So, yeah, it would be even greater if the slope was steeper, right? Yep, absolutely agree with you. And now, unfortunately, one of the conditions for me being allowed to show these questions, according to OCR, was that I had to show all of a question in its entirety. So here's another part of the question. Possibly. Yeah, I didn't think that far ahead, Freya. I just dropped some silly little clip art pictures down. Here's the last part of the question, but we're not going to answer this part of the question because I don't have time and it's absolutely irrelevant to the topic that we were covering. So, Wombat, why wouldn't force increase? Surely there's less friction. The friction is going to depend on how fast we're travelling. We're travelling the same speed, so the friction is exactly the same, Wombat. The gravity component, the component of gravitational force acting down the slope will increase as the slope gets steeper. And next session, next week, we're going to look at vectors, and you're going to see why that means the resultant decreases. But no, I'm not doing this question because it's nothing to do with the topic we're covering. But I've shown it here so that OCR can't accuse me of breaking their rules for copyright. Okay, and that's it. Well done, everyone. You managed to get through a Sunday morning. You chose to come here for a Sunday morning when you could have stayed in bed to do all sorts of extra physics, doing some calculations, doing some maths. That is absolutely wonderful. I'm over the moon that you did this. So next session's going to be about vectors. Do tune in. If you haven't done so already, please do like and subscribe. I don't care how cheesy that sounds. And do let all your friends know they should join in. And I will see you all next week. If you have any questions during the week, get on Facebook, send me the message, and I'll see if I can deal with those next week. Okay. Thank you very much.